Greetings everyone. My name is Siddharth Mishra and in this video we will be learning about radial and transverse velocities. First of all, consider an initial line OX such that O represents the origin. Now this is the line with respect to which we will be measuring all the positions. Consider a particle which is moving in a path something like this. Suppose that the position of the particle at some time t is at P with polar coordinate r, theta. That is, point P makes an angle with the initial line OX with measure theta, and obviously the distance OP is r. Now suppose that in a small interval delta t, this particle travels to some point Q. Let us assume that Q has polar coordinate r plus delta r and theta plus del theta, which means that OQ is equal to r plus del r and angle QOP is del theta. Now, the expression of radial velocity is given as follows. Radial velocity at P is given by limit del t tends to 0 displacement of particle along OP over time del t, which means that when the particle travels from P to Q, its image on the line OP, which we are going to extend, tends to move from P to some point M such that QM is perpendicular to OP. For easier understanding, assume that a viewer is observing this particle move from here, and when he will see the particle moving, it would assume that the particle is moving from P to M with a certain velocity rather than P to Q. So here angle QMP is a right angle. So let's start deriving the formula for radial velocity. Let us represent radial velocity with VR. So VR is equal to limit del t tends to 0. Displacement of particle along OP is obviously PM. So it is given by PM over del t. Now we can write PM as OM minus OP over del t. This expression can also be written as limit del t tends to 0. OM is here obviously OQ cos del theta. This thing is derived from by using trigonometric ratios, because cos theta is equal to base upon hypotenuse. So obviously base is equal to hypotenuse multiplied by that cos of theta, and we know that OP is equal to OP itself. Let me just put all these values in the next step. So VR becomes equal to limit del t tends to 0. OQ is equal to r plus delta r. We can see this in the figure, and let cos theta be it, and OP is equal to r whole upon delta t. Now expansion of cos theta is as follows. Let me write the expansion of cos del theta only. It will be given as 1 minus del theta square over 2 factorial plus del theta to the power 4 over 4 factorial and so on. Now, obviously, since del t is tending to 0, therefore q is tending to p, or we can say that these 2 points will come together as we will decrease the time interval. And once at one point they will be so close to each other that del theta will be approximately equal to 0. And so all these value of cos del theta will turn out to be 0, which have greater indices of del theta obviously, and we will obtain cos del theta is equal to 1. So now we can write that Vr is equal to limit del t tends to 0 r plus del r multiplied by 1 minus r over del t. R's cancel out and we will be left with limit del t tends to 0 del r over del t, which can be written as dr over dt. Therefore, we obtain the expression for radial velocity, that is Vr is equal to dr over dt, or we can say that the radial velocity at a point is the first derivative of radial vector or radius of that curvature, and it can also be written as r dot. Now let's move on to transverse velocity. Let me clear the screen. Now, transverse velocity. Let us move on to the same diagram first. Suppose that an object is moving in a curve like this. At some time t, it is at point P, which has polar coordinate r theta, and at some time t plus delta t, it is at point Q, which polar coordinates r plus del r, comma theta plus del theta. Now, we assume that the particle was moving along the direction of OP in radial velocity obviously. But in case of transverse velocity, we are going to measure the velocity of an object at the rate it is transcending from M to Q. So for that, suppose that a person is standing here, and when he will be observing this particle moving, it would feel like that the particle is moving from M to Q rather than P to Q. So transverse velocity Vt is given by limit del t tends to 0 displacement of particle along particle perpendicular to OP over del t, which can be written as limit del t tends to 0 qm over del t. Now qm can be written as OQ sine of del theta over del t. We know that from the figure, OQ is equal to R plus del R, and the expression of sine theta is as follows. Sine theta is given by del theta minus del theta cube over 3 factorial plus del theta to the power 5 over 5 factorial and so on over del t. Now, as del t tends to 0, del theta tends to 0 as well, So therefore, uh, all these expressions with greater indices of del theta will become 0. Now they don't actually turn out to be 0, but they become seemingly negligible. But we will not neglect del theta because it is not very small as compared to all these things. So let us conclude, and also sine del theta. If you have gone through limits, limit del theta tending to 0, sine of del theta is del theta obviously. So limit del t tends to 0, r plus del r multiplied by del theta over del t. Now product of del r and del theta can be neglected. So this can be written as limit del t tending to 0, r multiplied by del theta and del r multiplied by del theta, which we are going to neglect. So we will not write it here, and this is what we obtain in the end. So it implies transverse velocity can be given by r d theta over dt. We can also write it as r theta dot. So we conclude here that the expression for transverse velocity is r d theta over dt, and radial velocity is r dot or dr over dt. Thanks for watching.